All right, let's talk about golden rectangles. They're kind of neat. So, what's a golden rectangle? Well, we need to talk about a process. I have something in mind. I take a rectangle, any old rectangle, like so, and so I'll call that side A. This is called side B, and I'll have B always be the shorter side. So because it's shorter, that means that there's some length along here, which is also B. And I can just draw in this, and I get a square. So this is B squared. And this is some leftover amount. Okay, great. Now, this kind of looked like I made two squares. So I'll shorten this rectangle so that now we have a short rectangle with side lengths B and C. Now I do the same thing again. I take that C length and I kind of go up here and I make a, so this is all C. And now I've got another rectangle, and then I pop out that kind of square, this sort of like that, DD, and I make another rectangle, and I keep on going as well as I can. So it pops out to the right, pops upward, then pops to the right, up, right, up, right, up, carving out a square from these rectangles for as long as we can. The question is, how long can we keep on doing this forever? Is there something about rectangles that are special with regards to this process? And so I'm going to go over to GeoGebra now, and basically I've got a rectangle here. Boom. Beautiful, beautiful rectangle. Now I'm going to put in the square, which I've already done, quadrilateral 2. So here's a square and here's a rectangle, right? And then, as I shorten this length, you can see it gets more different from having two squares to having like a thin, narrow rectangle. And if I go to the right, I actually have the leftovers longer than the stuff I removed. So I could put in another square. I'm not doing that. But let's go back to this this view here. And now I take out that next square. Okay, so now I've got a square, I've got a very narrow rectangle here. And so I do it again. And there you go. And so I still have a narrow rectangle, but notice that I could probably put lots of different boxes in there if I wanted to, of that same size. And the consequence of that is that the next one goes outside the boundaries. All right. So what did it look like if, so things get kind of worse as you get further above 2. Things start to be looking like they're improving as I get closer to like around 1.7 to 1.6 area is really great. 1.5 is looking okay, although it's probably going to be dodgy the next time around, because look at this. Boom, right? Too small. And then, so I can increase it back up. 1.6 is looking good. I can still continue this process. And there we go, get another one. Basically, from this exploration alone, I'm already kind of, this thing's going to stop if it's greater than 1.63. or less than 1.6. And you can kind of see, like at 1.6, it stops entirely, whereas when you go beyond that, it kind of breaks out, right? Okay, so that is the little exploration of GeoGebra. Now we'll go back. So what are we looking for? We're looking for a rectangle where I can keep doing this process without a problem. And so one way to, perhaps the only way, to ensure this is that you get a copy of the original rectangle itself, smaller, but the same dimensions. And then you can keep on doing it, right? Because you're always going to, if you could get a square in there the first time, then with the new rectangle in the same dimensions, you can still get the next square, because it's always going to have that reasonable bit. And so you're never going to get that leftover remainder to be too big. That's kind of basically what happens. So going back to the little sketch here, what do we need? So I'm just going to take out this inner thing here, right? And so we have rectangle AB, and then we have another rectangle. The next one is BC. So the long side is B, short side is C, theoretically. But C is the one that we're going to use to make the square, so that's the relevant one. For the second rectangle, and the first rectangle is B that we use to make the square. So now we want BC to be a scaled copy of AB. It's just a little miniature version. Well, what does that mean? That means that basically there should be a number R such that we multiply A by R and we get B. I mean, that's always going to exist. But then here's the special condition, is that that same number, when we multiply B by that number, gives us C. Actually, let me just verify which one. So I'm either going to get R or the 1 over R of what people always talk about. And I guess what I want to do is, well, okay, this is not what I want to do. Sorry. What I want to do is A equals RB and B equals RC, so that the large side over the small side is equal to this ratio, and that's supposed to be over here too. All right, good. Now we also have, because of this picture here, this is just how C is kind of defined as well. So we have a process taking out the square. This defines the C that remains, and B plus C should equal to A, right? That's just, it's part of it makes up that two sides. And then we're imposing the condition that we're getting the same rectangle, except scaled down. So the sides are in the same ratio, same proportion. Well, so A equals RB and B equals RC. So we take this, and we take this, and we combine them. So replace B with RC, and then over here, replacing b with rc gives us r squared c. Ooh. R squared c, and that should be equal to 1. Oh, oops. Yeah, that was not right. RC plus C equals, now we replace A with R squared C. That's the one. All right, now C is some number, but it's common to each of these terms. So we're just going to divide by C. If C is 0, our process didn't create a rectangle, and so it didn't create a copy of this other rectangle. It's a little bit of a fudge because, of course, there would be a number r that, namely 0. Well, I guess no. I mean, these relations wouldn't work, but the you know, it's like, I mean, it's kind of a scaled version of the original rectangle 0, right? It's just not there. Imagine any way you want, it's not there. But anyway, it's an edge case that doesn't concern us because we don't care about that, because we want to keep doing this process. We've run out of space, so forget 0. 0 is always a problem. Okay, r plus 1 equals r squared is our equation to solve. All right, so right off the bat, we know that there's at most 2 solutions. So this process with getting the same rectangle again going down, that only has 1 possible or 2 possible solutions already. That's what this is saying. As it turns out, we only have 1. So what is this thing? So r squared minus r equals 1. So I've put the r on the other side. I did that because I like to factor things this way. R squared minus r is equal to r times r minus 1. So that suggests that we have a parabola like this. Goes through 0, goes through 1. There's a point below. It's an upward facing parabola because the coefficient in front of r squared is positive. We draw in this parabola. There we go. We're looking for where it's equal to 1, right? So that's bad solution, because the dimensions of a rectangle are always positive numbers, so we don't want that negative. So now we're down to just 1 solution. Haven't really done much computation. What was this vertex here? Well, remember that this is halfway between the 2 roots. So it's at 1/2. The 2 roots are at 0 and 1. 0 because putting in 0 makes this term 0, which makes that 0. And then putting r equals 1 into that factor gives us a 0 as well. So halfway between that is 1/2. Okay, so that's kind of my little thinking process there. And now if I plug in 1/2 into there, I'm plugging 1/2 in for r, okay, and then 1/2 minus 1 minus 1/2. Notice how it's that x location times itself, you know, with a possible minus sign, right? Here it is a minus sign, so it's minus 1/4. So this is 1/2 and minus 1/4. Excellent. So r squared minus r is equal to r minus 1/2 squared minus 1/4. And we're trying to set that equal to 1. So that's what we got to solve. Just so I've done it. Just to verify that what I've done, let's see, what is this? This is minus So if I want to square out the r minus 1/2 squared, I could do this. Here's a nice little square. R squared minus r over 2 minus r over 2, and then plus 1/4. So sum that up, I get r squared minus r over 2 just becomes minus r, and I have a plus 1/4. And then I have, of course, this minus 1/4 here. So that cancels, and I'm left with r squared minus r. So I'm good. Excellent. It's just a little check. Anyway, back to the equation solving. I add 1/4 to the other side. R minus 1/2 squared equals 5/4. R minus 1/2 equals the square root of 5 over 2. Square root of 4 is 2. The square root of a fraction is the same as taking the individual square roots, as long as everything's positive. Also, when you take square roots, you don't know the sign of it, so it's plus or minus. Here, which one would it be? Well, essentially so r equals 1/2, and it's going to be the one to the right, just by the picture. So this thing is to the right of that vertex, so we're going to want the plus, because that's what adds to it. You can also check that the negative gives you a negative number, but anyway. So 1/2 plus root 5 over 2. All right, and what is 1/2 plus? So 1/2 plus square root of 5 divided by 2. Now, before I do this, GeoGebra kind of suggests it was going to be somewhere around 1.62 where this process works out well. So that's hopeful. What is the square root of 5? It's a little over 2, maybe like 2.2. We're dividing by 2, right? So that's like maybe 1.1, and 1/2 is 0.5, so that's like 1.6. So expect something in the 1.6 neighborhood. And I have a nice little answer. There we go. 1.618033989. Beautiful. By the way, the mode on this thing, I guess normal. Oh, answers decimal. You can decide decimal or fraction and significant figures. And if I go back to second entry, enter, now it just gives me the decimal. Okay, great. So approximately 1.618. Yep. All right, so that's the golden ratio. That's what it means. And it means that you can do this self-similar process of removing this square. It's kind of neat. The fact that it has that kind of nice property kind of suggests that kind of a lot of self-similar sort of processes might tend to gravitate towards that, because it can keep on going the closer it gets to the golden ratio. This is the golden ratio. Okay, and so that's nice. There's also something called Fibonacci sequence, where you're doing something and the golden ratio pops out of that. People love to talk about it. It's kind of cool. People think it's kind of nice aesthetically. I don't know about that. And what else? Oh, what about 1 over r? So is there something special about 1 over r? Well, of course, we can just try to compute it by reciprocating what we have. That's not very interesting. But remember, we had r squared minus r equals 1, right? So if I divide everything by r here, I get r minus 1 equals 1 over r. So what does that tell me? So that tells me that 1 over r is actually equal to 1/2 plus square root 5 over 2 minus 1 equals minus 1/2 plus root 5 over 2. So I didn't actually have to flip it, just compute it. And if I were to go one step further, divide by r again, I would end up with 1 minus 1 over r equals 1 over r squared. Now if I introduced s equals 1 over r, just all these names, just names, I'd have 1 minus s equals s squared, or 1 equals s squared plus s. So that's sort of the reciprocal of the golden ratio, the smaller version. And so those are s's. I should avoid s. That's just another simple equation that's involved in this stuff. And the parabola for this thing looks kind of like this. And so it's shifted. It's a shift of that parabola by 1, which is what the thing before just basically said in terms of finding the roots. You got the vertex at minus 1/2 and minus 1/4. Do all that same thing. All right, so that's the golden ratio.